Good morning, students. Today I am going to explain you the fundamental theorem of algebra. The statement is a polynomial of degree n with complex coefficients has n zeros in C. A polynomial of degree n with complex coefficients has n zeros in C. I think you are all familiar with the polynomial, isn't it? Of degree n with the complex coefficient. Coefficient of the polynomials are all complex numbers. Okay. Now, proof. Let a0 a1z plus a2z square plus etc plus an z power n, where an not equal to 0, be a polynomial of degree n. So I have taken a polynomial of degree n. Here I have insisted that an not equal to 0, because if an equal to 0 means this term will vanish and z power n will vanish. Therefore, the degree of the polynomial will be lesser than n. It will less down. Okay. So that we have insisted that an is a non-zero. Okay. Now, let us split this polynomial. That is, I am going to use the Rouch theorem, okay, to prove that it has n zeros. Okay. For that, I am going to split this polynomial. Okay. So this last term an z power n, I have taken that an z power n as a single function f of z. Okay. And the remaining terms from a0 to an minus 1 z power n minus 1 as another function g of z. Okay. So if we add f of z plus g of z, we again get this original polynomial star. Okay. So that I have taken this. Now let us view this one. What is the limit z tending to infinity of g of z by f of z? It will be 0, because you see here g of z by f of z. G of z is nothing but a0 plus a1 z plus etc plus an minus 1 z power n minus 1, and f of z is an z power n. If we divide term wise, we will be getting a0 by an z power n plus second term a1 z by an z power n. 1 z will get cancelled, and in the denominator we are having z power n minus 1. In this way, if we go on term wise division, we will be getting on the last term an minus 1 by an z. Okay, denominator will be having z. So if limit z tends to infinity means every denominator we are having z. Therefore, in the denominator it will be infinity. So that it will, the first term will be 0 tending to 0 plus 0 etc. Last term will also tends to 0. So sum of these zeros will again give us 0. Okay. Therefore, limit z tending to infinity of this quotient function is 0, which means this is a bounded function. This is a bounded function. Also, if we view f of z, it is a polynomial, and g of z is again a polynomial. We know that every polynomial are all continuous functions. Okay. Therefore, this function is a continuous and bounded function. Okay. So by maximum modulus theorem, there exists some real number. Okay, in the boundary. So above is g here. F of z by g of z tends to 0 as z tends to infinity. That is, if we give higher values for z, greater values, this quotient function will tends to 0. Okay. So at some stage, okay, that is modulus of z greater than r, this function will be lesser than 1 value. It will take less than 1 values. Okay. So that only we are having this statement. Hence, there exists a real number r. This r denotes this one, the value for z. Okay, mod z greater than r. For this values, this function will take lesser values. Okay, so modulus of g of z by f of z will be less than 1 for all z with mod z greater than r. Hence, by Rouch theorem already sent. I have sent to you an YouTube explanation to you, so that you will be familiar with that. If not, then you go through. It is a previous theorem for this one. So it is theorem 8.3. Go through that once or twice, then you can compare that, and then you can analyze how you are applying here. Okay. So by Rouch theorem, we are having to apply the Rouch theorem, everything is satisfied. Therefore, we can use the statement which I have proved in the Rouch theorem, that states that f of z and f of z plus g of z. Okay. The denominator function here. Okay. How many zeros it is having will be same as the number of zeros for the sum of the numerator and denominator functions, namely f of z plus g of z. Okay. Therefore, by Rouch theorem, f of z and f of z plus g of z have the same number of zeros inside the circle mod z equal to r plus 1. Okay. Now, let us see f of z. What is f of z? F of z is just an z power n. You see here obviously z, if we put z equal to 0, f of z will be 0. That is 0 is a 0 for f of z. Also z is the power of n. Therefore 0 is a 0 for multiplicity n. 0 is the multiplicity n for f of z. 0. Okay. 0 is the 0 of multiplicity n. Okay. Hence the given polynomial, okay, f of z plus g of z must also have the same number of zeros as f of z. That is, it also has n zeros. Okay. Therefore f of z plus g of z is nothing but our given polynomial. The given polynomial has n zeros. Hence the proof. Okay. Okay. Thank you, students.